Yeah, good afternoon. It's my pleasure to welcome you to this webinar organized by the Technical Area Committee entitled Signal Processing for Multi-Sensor Systems. This is a Technical Area Committee of the EURASIP, European Association for Signal Processing, that's EURASIP. And my name is Marius Pesavento. I'm sharing this webinar today, and we are featuring a talk by Professor Stephan Weiss from the University of Strathclyde in Scotland, UK. And just briefly, Stephan Weiss received his Diploma of Engineering degree from the University of Erlangen-Nuremberg in '95 and a PhD degree in signal processing from the University of Strathclyde. And after some academic positions at Strathclyde and also the University of Southampton, he returned to Strathclyde in 2006, where he's currently a professor. So his research interests include adaptive multi-rate and array signal processing, and in particular with some of his collaborators, he has championed the work on polynomial matrix methods, and this is also the topic of today's webinar. So I find these methods quite useful for actually many different applications, and I hope you will enjoy this talk today. So during the webinar, you are able to write some questions in the chat, and we will address them at the end of the talk. And you will also be able to ask questions, of course, at the end of the talk. Just raise your hand then. So without further ado, I would like to hand over to you, Stephan, for your talk.
Marius, thank you very much, not just for the very kind invitation and the words that you have said. I'm really grateful for the opportunity to share this with you and the attendees of today's webinar. Just to give you a little bit of background of why we deal with matrices of functions and who's involved in this. So the whole work started actually more than two decades ago by John McWhirter. Originally, his group at the Royal Signals and Radar Establishment looked into, latterly Kinetic, really looked into solving the broadband blind source separation problem. And as part of that, they came up with an algorithm for polynomial matrix decompositions called the SBR2 algorithm, which I mentioned later on. So since that time, there's a group of us who've been looking further into this work and supported particularly by two larger projects funded by our EPSRC, the Research Council in the UK, and the Ministry of Defense over the past 10 years. We've accelerated this work in terms of algorithmic solutions, but we've also been looking into the underpinning theory and been expanding on the applications. So instrumental in that, particularly in the theory part, were Ian Proudler and Jen Pestana, who I've kind of depicted here as well. Unfortunately, I didn't include any pictures of more recent collaboration. So it's particularly the Imperial College group on audio signal processing by Patrick Naylor and his researcher Vincent Neo, who made excellent use of these techniques in the speech domain and developed some very, very nice applications of that. And that's drove and motivated us really much further. So over the years, there have been quite a number of researchers, PhD students, and collaborators involved. And I'm not going to read them all out, but you see this, it's not just a single effort by myself. There's been a lot of people involved in this. So to give you an idea of what I'm going to do with you over the next 50 minutes or so, so if we've just had the background overview, I'm going to chat to you a little bit about where we encounter matrices of functions and what this is. So it can be quite ubiquitous. We look at some basic properties and operations that we can perform in such constructs, and this will then lead to formulations for broadband problems. So broadband means not broadband internet connection, but broadband in the sense of perhaps signals that span several octaves and that you certainly cannot consider as narrowband anymore. Now, the solution to a lot of these broadband formulated problems are given by matrix decompositions of the type that John McWhirter initially addressed. And this is my next section of the presentation. I'll follow this up with some applications. So to get started, I'll show you a little bit of where you can encounter matrices or functions. I'll show you this in the communications context, filter banks, and also in the context of statistics. So if you imagine you have, say, as you see on the right-hand side here, a system with 2 actuators and 2 sensors, then each actuator sensor pair is spanned by a transfer function. And if you now write this 2x2 system as a matrix, then immediately you have a matrix that depends not just on real or complex gain factors, but actually on transfer functions that depend on the complex variable set in this case. So these functions can be quite arbitrary. They could be polynomials, so FIR type filters. They could also be infinite impulse response systems, and typically you might represent these as rational functions, but it can be a lot more general as well. They can be transcendental, so they can be infinite series that you may not even necessarily be able to express as a rational function. But the key element is that we'll demand that these functions are analytic, so they will decay at least as exponentially, and that has a quite profound impact on what we can do with them. So just in terms of these functions, there's Laurent series, which are infinite and decay in both positive and negative time. Laurent polynomials are truncated Laurent series, so they will not go to infinity. And finally, there's also series or polynomials, so power series of polynomials, which are either strictly causal or anti-causal. And again, the power series would be of infinite extent, and the polynomial would be finite. So it's these type of functions that we will concentrate on, and basically any analytic function you will be able to represent either as a Laurent series or a power series at the very least. And I'll talk a little bit later about approximations of these functions as well by, for example, finite impulse response filters or polynomials that are easier to handle. So if you now have this image in your head of this matrix of transfer functions, you could also look at this in the time domain. So you have a 2x2 system of impulse responses, for example, right? So you have a matrix H of n. This is your matrix of impulse responses, and through a set transform, you get to the transfer function matrix. So this would be in the communications context. If you maybe have a background in filter banks and have constructed these before, you might, for example, take a signal, you split this into a number of different frequency bands, and because of the band limited nature, you can then decimate, ideally critically by a factor of k if you have k of these filters. Then you can bring this into what's called a polyphase representation. By swapping the decimators and the filtering operations around, you would first go into the decimator, so you demultiplex your signal here in the bottom, and then you go into a network of polyphase components, and this network of polyphase components typically is represented through a polyphase analysis matrix, right? So these elements of your matrix are again transfer functions, and these transfer functions relate to polyphase components or subsampled components of your filters in the top diagram. You can do the same thing with a synthesis filter bank, so the dual operation that tries to reconstruct your original full band signal from the subband signals, and you can also use a polyphase representation. So in this case, you go through a polyphase network first, your polyphase synthesis matrix, before you perform a multiplexing operation to tie your full band signal back together again. And if you now imagine these two constructs of the last two slides working back to back, so you have your demultiplexer, you have your polyphase analysis matrix, the polyphase synthesis matrix, and the multiplexer, then you basically, if the inner part multiplies out to an identity, then the multiplexing and demultiplexing operation is transparent as well. So we really demand ideally what we see here in equation 2. We can relax this a bit in practice, but typically we would like to perhaps find a synthesis matrix that performs a perfect reconstruction. That means we'd like to have the inverse of a polynomial matrix. And there I already have the desire now to perform a linear algebraic operation on a matrix of functions in this case. So the third area where you might encounter polynomial matrices is in the context of multi-channel signals and their statistics. So imagine that you have a measurement that comprises of data from M sensors. So you have a measurement vector X. Then, for example, the angle of arrival of sources that illuminate this array will be encoded in the delay with which these signals arrive at different elements of your array. Right? In the narrowband case, these delays shrink to phase shifts, but if we have broadband signals, then we really have to preserve these lags between with which these delay components with which the signals arrive at different sensor elements. So in order to account for this, we define what's called a space-time covariance matrix in equation 3. So whenever I try to highlight something, I move forward in the slide. So I'm not trying to highlight, but I hope you can see my mouse pointer. So we have the expectation of our data vector multiplied with its Hermitian transposed and delayed version by Tor samples. So this space-time covariance matrix now would be an M by M matrix, but it also has a lag component. So again, it's not a matrix that contains real or complex valued coefficients. It's a matrix that now contains auto and cross correlation sequences of your signals. And for a 2 by 2 example in equation 4, you see on the main diagonal of this matrix, the two autocorrelation functions of your two signals, x1 and x2. And then the two off-diagonal components, you have the cross correlations between signal 1 and signal 2, and between signal 2 and signal 1. And because if you change the arguments of a cross correlation function around, right, you basically take the time reverse complex conjugate of your cross correlation function. There's interesting symmetries in this matrix. Right, so this defines a little bit about where we encounter these matrices. So if you now take, for example, the Z transform again of that space-time covariance matrix, we end up with what's called the cross-spectral density matrix. So in the main diagonal, we would have power spectral densities and cross-spectral densities in the off-diagonal terms. And what you see in the figure on top here is actually still a depiction of the time domain. So this is your 2 by 2 example matrix. On the diagonal, you have the two autocorrelation terms. They're symmetric in the real valued case. And if you check the bottom right-hand corner element, this will be the time reversed and potentially complex conjugated component in the complex valued case of what you have in the right-hand corner of your matrix. So this is now 3 examples of where you encounter such matrices, and I'm sure you can find many more where such a matrix description is actually quite compact to describe a problem. So I'd now like to define a few properties and operations of such matrices. That's quite centrally the para-Hermitian properties that particularly applies to the space-time covariance matrix. We also define a para-Hermitian transposition. We define an extension of the unitary property for complex valued matrices. And I'll talk a little bit about analytic functions as well, because that's quite central to the matrices that we consider here. So for real and complex value signals, you can do a transposition or a Hermitian transposition of a matrix. And for matrices of functions, there's something called the para-Hermitian operator. And the para-Hermitian operator kind of takes one more step. It performs basically a transposition, complex conjugation, as you would expect from normal matrices. But on top of that, it also performs a time reversal. So you, for example, see a matrix A of Z on the top. And if you take this para-Hermitian, so that's A sub P, I'd like to call this the Proudler operator. So that works similar to Hermitian transpose, but does a time reversal as well. Then you see below, we basically do a transposition. We flip the matrix along its diagonal, but we also perform a time reversal. So if you look at the red element, bottom left-hand corner and top, that ends up in the top right-hand corner below, but in a time reversed fashion. And if it was complex valued, we would see a complex conjugation of that term as well. Right, so this is the para-Hermitian operator. Now there's a para-Hermitian property as well. So if you go back to standard matrices, you can do a Hermitian transposition, but you also have a Hermitian a Hermitian matrix, which is an extension of the symmetric property of a matrix to complex valued matrices. So if you have a Hermitian matrix and you transpose complex conjugated, you actually end up with the same matrix again, right? So a Hermitian matrix satisfies these properties, and the para-Hermitian matrix similarly satisfies this property of being identical to its para-Hermitian. So crucially, space-time covariance matrices are para-Hermitian matrices. So below you see an example, right? So you have symmetric functions like autocorrelation functions in the main diagonal again, and the off-diagonal terms that are symmetric here with respect to the diagonal, they're time-reversed versions and potentially complex conjugates of each other as well. So a matrix that satisfies this property of being identical to its para-Hermitian is called a para-Hermitian matrix. One more important property is para-unitarity. So there's a lot of para things flying around here. You're familiar with the unitary property. So unitary matrix has basically orthonormal rows and columns, and the inverse of the matrix is just identical to its Hermitian transpose. So we have something similar for matrices of functions, and if you multiply a matrix here in equation 6 with its para-Hermitian, and if the matrix is unitary, then this product simply gives you an identity. So in this case, it's very simple to find the inverse of a matrix, because the inverse of a para-unitary matrix is simply its para-Hermitian. And if you return to the earlier problem of constructing a filter bank, where I said the synthesis, the polyphase synthesis matrix should be the inverse of the polyphase analysis matrix. If that matrix is para-unitary, it's very easy to immediately state what the perfectly reconstructing synthesis matrix is. So this is important because it preserves energy. So similar to the unitary matrix, preserving, for example, a norm of a vector, the Euclidean norm, a para-unitary matrix is essentially a lossless filter bank. So it shuffles signal components around, but it doesn't lose anything, right? So this is kind of embedded in this idea of being a rotation and basically being able to recover the original an original signal vector simply by performing the para-Hermitian operation. Right, so since we deal with matrices of functions, let me just say a little bit about the type of functions that we're looking at as well. So in the widest sense, we're looking at Laurent series. And as I mentioned before, we look at analytic functions. So in the context of Laurent series, these would be series that decay in both positive and negative time, at least exponentially. So as such, they're absolutely summable and their set transform exists. But there's a couple of more profound aspects from this as well. So there's things like the uniqueness of analytic functions. So if you have two functions and they agree on part of the region of convergence, they actually have to be the same. So this will define some uniqueness later on of decompositions that we find of matrices of functions. Also, if we don't want to deal with functions that potentially decay in both positive and negative time, that's acceptable if you have, for example, auto and cross correlation sequences. You expect that they decay in both positive and negative time. But if you come up with a filter design and you want to implement such a system as a filter, then ideally you want to have it as perhaps it's an FIR type system. But the best least squares approximation of such an analytic function, such a Laurent series, is basically achieved by shifting and truncating. Right? And it doesn't matter what accuracy you want, it's really the truncation that does the best least squares approximation here. And in principle, if you allow a sufficiently high polynomial order, then you can approximate this Laurent series, this function, this analytic function, as closely as you want. Right, so this is basically depicted here. You have the Laurent series from the previous slide. We've shifted this a little bit to the right, and you also see that we've now zeroed the anti-causal components, and we've truncated here in positive time. So we performed an approximation of this Laurent series by a polynomial. So this kind of concludes what I wanted to say about operations and properties of matrices or functions. And I'd now like to move on to what really matters to us. And this was using actually these functions, these matrices or functions to formulate and later on to solve broadband problems. Yeah, broadband multi-channel problems, I should say, because we deal with signal vectors here. So I'll show you three kind of cases of where we can do these formulations from slightly different areas. One is in communications, MIMO system decoupling. We look into beamforming, and we have a general kind of slide of how we would move from narrowband to broadband formulations. Okay, so in a MIMO system, for example, if you know your MIMO channel impulse response, in the narrowband case, the best type of pre-coding and equalization that you can do in various senses is to use the singular value factors, the SVD factors, as pre-coder and equalizer matrices. There's various nice aspects about these. That they're unitary, right? So in the transmitter, they don't change your transmit power. In the receiver, they don't amplify the noise that you have sitting on your antennas, for example. So the fact that these are unitary matrices is quite beneficial. And you can now take this to the polynomial domain. So you don't just have a matrix of complex gain factors. You maybe have impulse responses because your symbol period is shorter than the coherence time, or the delay spread of your channel. You have multipath propagation. So you really have a matrix now of channel impulse responses, and you want to not deal with OFDM. You want to perhaps deal with a single carrier fashion. And this means that you now need to have precoding and equalizer matrices that actually operate for every value set and can diagonalize this type of system, right? So you basically look for an analytic or polynomial version of this SVD. If you look into array processing, and particularly into beamforming, let me just put the following situation to you. So what you have on the right-hand side in this figure, you have your measurement vector of capital M signals. So these are the array, that's the array signal that we have. And we measure the source U of n. So this source illuminates the array through a number of different impulse responses. So even every one of these blue arrows just looks like array, right? This A1 of n is an impulse response and could be arbitrarily complex. So it could be a rich scattering environment. So if you now want to characterize the signal vector that we have received, in our vector x of n on the left-hand side is the convolution of a vector of channel impulse responses with our source signal. And if you take the set transform, then this is a vector of transfer functions. I mentioned that this could be a very rich scattering environment. In the simplest case, even if a free space propagation, the filters that you obtain from this are fractional delay filters, so they still have a substantial length generally. Right, so what you now would like to do is you'd like to have some filters that operate on these array signals and perform some coherent combination or perhaps a destructive interference of your source signal U of n, right? So you have a more complex scenario in this slide. We actually now have two sources. We have this signal U of n from the previous slide. let's say that's the one we want to coherently combine. But we have a second source signal as well, the signal V of n, that illuminates our array over this red path, which we would like to null out and suppress. If that was a narrowband scenario, you would probably have tools at hand immediately, right? So you can formulate the gain vectors, you can set up an equation. You can say, for example, well, my coefficient vector multiplied with the steering vector A should be 1. So I want to have constructive interference. And for my second source through this vector B of transfer paths, I would like to have a 0, right? So you can basically set up a system with two equations. You can solve this using a pseudo-inverse. And this is something that you might be familiar with. But you can now do the same thing using these matrices of functions. So we have vectors A of Z and B of Z. And if you find a pseudo-inverse now for this formulation here, multiplying this pseudo-inverse with a vector of 1 and 0, then we get the desired set of filter transfer functions for this type of problem, right? Okay, so this is from what we had from before, right? So we want to perhaps coherently combine one source. We want to null out another source. And we can do this if we know where our sources are located and what these transfer paths are. In beamforming, often the situation is not quite as generous to us. So we often don't know where our interferers are coming from, what the transfer functions are. So typically what we set up as a problem is a linearly constrained minimum variance problem. So you see that in the bottom left-hand corner. We want to minimize the output of our array. So the array is shown in the top right-hand corner. So that's the filter vector W Hermitian times the covariance matrix of our array signal times W in the narrowband case. So that's the output power of our array. And to avoid the trivial solution that all these filter coefficients are 0, we have to impose a constraint. And we demand that this filter coefficient vector gives us a gain of 1, at least in the direction of the known signal of interest. And if we know any directions of interferers, we can embed these into the constraint matrix as well. For the polynomial or for the matrix valued case, we have a very, very similar situation. We can define the output power. In this case, you involve the cross-spectral density matrix. You pre and post multiply this with the vectors of filters. And then if you integrate over the unit circle of this, you get the power as well. Yeah? So you know, integrate over the power spectral density gives you the power of your signal. And we can impose a constraint here in a very, very similar fashion, right? So we have a linearly constrained minimum variance beamformer in this case. So just to repeat, just at the top here, we have the narrowband solution versus the broadband solution, just to emphasize how these narrowband solutions generalize to broadband solutions. If we stick with this polynomial matrix solution, I'll just show you the capon beamformer below as well. So that's one way to solve this linearly constrained minimum variance problem. So on the left-hand side here, you have the narrowband solution that involves the inverse of your covariance matrix, the constraint matrix 3, and the right-hand side vector f of the constraint equation. And if you look on the right-hand side here, this is basically the broadband equivalent. The only thing you have to do essentially is that you turn every matrix into a matrix of functions. You turn what you have is a Hermitian transpose into a para-Hermitian operation, a para-Hermitian transpose, and you end up with the equivalent broadband problem. So just to summarize the operations that we perform, right? So in the previous section, I emphasized that we focus on analytic functions, and that allows us to focus on often a truncation, an approximation of these by polynomial matrices. So these are the simplest cases that we have, but in principle, we can deal with arbitrarily complex type functions as well. So with infinite series, and particularly with transcendental functions. But it's interesting to maybe take a step back and compare this to what you know in terms of linear algebra from real and complex valued matrices. Because if you ask the mathematicians, they will say that the matrix valued case is the function valued case is just a simple extension of what we already know from real valued and complex valued. So if you, for example, perform a transposition for a real valued matrix, you do the transpose. For a complex valued matrix, additionally, you do a complex conjugation. And for the function valued case, we additionally, on top of all of these operations, perform a time reversal. If you want to preserve energy, then in the real valued case, we demand orthonormality. That turns into unitarity in the complex valued case and to para-unitarity in the function case. And in terms of interesting structures, so what we discussed in terms of the space-time covariance matrix, yeah, so symmetry in the real valued case turns into this Hermitian symmetry in the complex valued case and to the para-Hermitian matrix in the function case. So with these kind of equivalents, it turns out that a lot of narrowband problems can be extended to quite simply to the broadband case. However, what is not immediately clear is because once you have this formulation, obviously you would like to solve these problems as well. In the narrowband case, solutions often hinge on diagonalizations of matrices, particularly on the eigenvalue decomposition, but also the singular value decomposition. However, if you perform an eigenvalue decomposition to, say, for example, the space-time covariance matrix, that depends on a lag component, then we can only diagonalize this matrix for one specific lag, but not for all the others. So what we would like to do is we'd like to diagonalize such a matrix of functions, not just for one component of tau or for one particular complex value set, but for all of these values. And this is going to be our next section. So I'm going to particularly look at the eigenvalue decomposition, although this has started to expand as well to other type of factorizations like the singular value decomposition, QR, and further linear algebraic operations. So I'm going to talk about two kind of more theoretical constructs. One's called the analytic EVD. The second one is an approximation, the polynomial EVD, which relates to what John McWhirter initially came up with as an algorithm. And then I'll just very briefly highlight three groups of algorithms for these type of decompositions. Right. So to start with the analytic EVD, this really goes back to someone called Franz Ehrlich, who worked in quantum mechanics and in mathematics for quantum mechanics. And he was interested in what happens to the eigenvalue decomposition if you perform a small perturbation to a covariance matrix, right? So your covariance matrix R now depends analytically on a parameter T. T is real valued, and on a certain interval, what you'd like to have is that you a small change in your matrix R will also only result in a very limited small change in both your eigenvalues and the eigenvectors of that matrix decomposition. And he showed that this exists. So for a self-adjoint matrix, so basically if the matrix is equal to its Hermitian transpose, he showed that there's in fact an analytic decomposition possible. And a couple of our signal processing colleagues did this in the last millennium also for the singular value decomposition. But these are essentially continuous time systems, if you like, so depend on a continuous real parameter on a certain interval. So what we can do now is we can use these results by Franz Ehrlich because our covariance matrix R will be analytic if the data that we consider is generated from sources through a set of transfer paths, so through some convolutive mixing by causal and stable filters. So if this is given, which in reality you'll find, then this matrix R of Z is going to be analytic in Z. So we can evaluate this on the unit circle, and we can directly apply the Ehrlich result and find this factorization. Yeah, a mistake that we initially made and was that we assumed that the decomposition should be periodic, but unfortunately it's not the case. So we treat omega as real valued, but what we really want is that these eigenvalues and eigenvector matrices are also 2 pi periodic in omega, such that we can resubstitute e to the power of j omega for Z again. And I'll give you a counterexample below. So the matrix R of Z that you have on the left-hand middle of the slide looks simple and innocent. But if you perform the eigenvalue decomposition of that, you see the eigenvalues on the right-hand side. They look quite good. But if you look at the horizontal axis, that's our normalized angular frequency, you'll see that these eigenvalues are actually periodic with respect to 4 pi. That means that the eigenvalues are analytic in the real parameter omega. But if you now bring this back into the Z domain, you actually end up with fractional powers of Z. So the equivalent to fractional delay filters. A fractional delay filter is like a sinc function or periodic sinc function. So the time domain decay is slower than exponential. These are not analytic functions anymore. Yeah? So while the functions are analytic on the unit circle, you can't extend them into the complex plane. So this is something that's connected to multiplexing. So the matrix that you had on the previous slide basically emerges through sending an uncorrelated unit variance signal through a simple filter, then demultiplexing the output and building the covariance matrix from these two signals x1 and x2. So it's multiplexing of signals that causes problems. And so basically an analytic EVD in the discrete time domain is possible, right? As long as we don't multiplex. If we have multiplexing by a factor of L, then we actually need to oversample the cross-spectral density matrix by a factor of L in order to admit analytic factors here. But if that's the case, right, if we have no multiplexing of our signals, then we can find this analytic SVD straight, well, it exists straight away, such that we have a diagonal matrix of real valued eigenvalues. So that's an extension of what you know from the EVD of Hermitian matrices. You have real valued eigenvalues, and you can select your eigenvectors to be orthonormal. So we have the same thing here. We can have analytic real valued eigenvalues in the unit circle, and we can select our eigenvectors to be to form a para-unitary matrix. So that's very comfortable. And the nice thing is that the eigenvalues are unique up to some arbitrary ordering, perhaps along the main diagonal. However, there's an ambiguity with respect to the eigenvectors. And this is perhaps not surprising, because if you take a look at the standard EVD of a Hermitian matrix, you also have a phase ambiguity of the eigenvectors. So if you think about writing down your analytic EVD on top here, you can basically introduce diagonal matrices of all pass filters, and you can multiply each eigenvector with an arbitrary all-pass function, and it will still be a valid eigenvector. So there's some ambiguity for the eigenvectors, but the eigenvalues are unique. Right, so now from this analytic EVD, back to what John McWhirter originally did. So he postulated that there was a decomposition, which I'd like to call the McWhirter decomposition, such that you can find a factorization of R of Z with polynomial or Laurent polynomial factors. So they're finite, hence the approximation sign. And an additional demand of this was that the eigenvalues satisfy a property called spectral majorization. So if you look at the eigenvalues along the diagonal of your matrix, you want them to be organized such that the top eigenvalue for every frequency component always has the highest value, the second eigenvalue, the second highest value, and so forth. So you see that as an example. On the left-hand side, you have a 3x3 matrix that's been diagonalized by one of John's algorithms. On the right-hand side, you have the power spectral densities, so the Fourier transforms of these eigenvalues. And you see that if you kind of cut across for any type of frequency along the normalized angular frequency axis, you always have the ordering that the top eigenvalue, the blue one, is the top one, the red one the second, and the yellow one should be the last. It doesn't always quite work out like that, but at least this is how spectral majorization is defined. Right, so how does this agree now with the analytic EVD? What's the relation between the analytic EVD and the McWhirter decomposition? And it turns out that if you have analytic eigenvalues that do not intersect, right? So that's the top right-hand corner case here, with the example of two eigenvalues, they do not overlap, then the two decompositions are identical. At the bottom left-hand corner, however, you see two eigenvalues that do intersect. And if you now demanded spectral majorization of these, then on some interval here, roughly between pi/2 to perhaps, not sure what this is, but my mouse points there. Yeah, in this interval, we should actually interchange the two eigenvalues such that the top eigenvalue always has the highest power and the second eigenvalue the lowest power. So in this case, the analytic and the polynomial EVD are going to differ. So what is the impact of this? I'm going to show you a numerical example, and we'll do this from a constructed matrix. So we've basically assume two eigenvalues, and we assume some very simple eigenvectors here. So eigenvalues have order 2, eigenvectors order 1, and if you multiply this out, we have a cross-spectral density matrix that satisfies this para-Hermitian property. So here's the two graphs, both over the normalized angular frequency axis. On top, you see the two eigenvalues, the analytic eigenvalues, so they're not spectrally majorized. You have one that's basically a raised cosine, the other one's a raised sine function. In the graph below, that's a little bit trickier. You have a characterization of what's happening with the eigenvectors. And what we do is we measure the angle at any type of frequency between our eigenvector and the reference vector, right? So this is a Hermitian angle that we measure, and this is what we display here for both the eigenvectors of our matrix. So because we take the Hermitian angle takes the modulus of the inner product, it looks like we have a non-differentiability here, but this really comes from the modulus. So what you see here is you have a smooth evolution of that angle between the eigenvectors. Okay, so if we now wanted to have the spectrally majorized solution instead, we have to flip segments of our singular values around. So we have to perform a piecewise analytic. We have to basically construct something from piecewise analytic functions. So in these two black dots here, we switch the two eigenvalues such that the blue one's always on top, the red one always has the lower energy. And because we switch the eigenvalues, we also switch the eigenvectors. So you see that below, we have over this interval also a flip of the eigenvectors. So what's the impact of this? We have a discontinuity for the eigenvectors. That's quite bad. And we have a non-differentiability for the eigenvalues, which is also not good, but not as bad as a discontinuity. So if you now apply some of the polynomial EVD algorithms that target the McWhirter decomposition, then indeed you actually converge to a spectrally majorized solution. And you might remember what the subspace angles look like. They also looked similar, but because we're now trying to approximate a discontinuity with polynomials, so with a finite length system, you get Gibbs phenomena and jumps here. Right, so let me have a quick look at algorithms with you. So I'm first going to look into PVD algorithms, so the polynomial EVD algorithms. the initial algorithm that John and one of the researchers, Soyden Rediff, came up with is the second order sequential best rotation algorithm, or SBR2 algorithm. And it's an iterative algorithm. You basically start with the covariance matrix and maybe imagine this matrix in the time domain. So the notation here is in the Z domain, but it really is a time domain method. So you have a matrix that now is an M by M matrix, but it has a lag dimension into as well. So you could almost think of this as a three-dimensional tensor. So the algorithm SBR2 works is a generalization of the Jacobi method, whereby at every iteration we target the largest off-diagonal element and try to eliminate that. The Jacobi algorithm works for a standard matrix. So in order to account now for the fact that these largest off-diagonal components might not necessarily be for lag tau equals 0, but somewhere else in the depth of that matrix, we have to apply a delay or advance first in order to bring these components onto the lag 0 part of the matrix. And then we rotate its energy onto the diagonal. And by doing that, we iteratively decrease the energy in the off-diagonal terms. So that's because the rotation that we perform for the energy onto diagonal is done by a Givens rotation that we don't just, you have to apply to every lag component of your matrix. We start undoing efforts again where we have performed eliminations already. But in general, you can prove that this algorithm converges and continuously reduces off-diagonal energy, right? So this is a really nice algorithm that's guaranteed to converge, even though initially it wasn't clear to John or to us what type of matrix decomposition this algorithm converges. Yeah, but now understanding the existence of the analytic EVD and how that relates to the polynomial EVD, we have an idea of that. There's a similar algorithm called sequential matrix diagonalization. So you again bring the largest off-diagonal component onto the lag 0 part of your matrix, but then instead of just using a Givens rotation, you actually perform a complete eigenvalue decomposition to transform the energy onto the diagonal. So it's more costly, but per step it transfers more energy. And there's quite a lot of different versions of these algorithms around with different search strategies, transfer of energy. So they have slightly different convergence properties. So I'd like to now focus on a new type algorithm that's operating the DFT domain, and that's basically capable of retrieving the analytic eigenvalue decomposition. So imagine that you have, for example, a system with 3 eigenvalues, and the whole benefit of performing the EVD and these polynomial, these matrices of function approaches is that we essentially operate in the time domain and we preserve spectral coherence. By now working in DFT bins, we can perform a simple EVD in every frequency bin, but we lose the coherence between these different frequency bins, right? So you see the eigenvalues on top, you see the bin-wise evaluation of the eigenvalues underneath, and with the picture on top, you might still be able to do the association. But if you now look at the bottom right-hand corner where I don't show you the continuous eigenvalues, it'd be very difficult to perform this association. So if you now perform a bin-wise EVD, then we have basically an association problem. We might have to do a permutation in every bin of our eigenvalue decomposition. So that's these terms PK, the permutation matrices. And we also have these phase ambiguities for our eigenvectors. So the algorithm that we've come up with first extracts the eigenvalues, which are less volatile. And it was Ian Proudler's idea to basically use a Viterbi type algorithm in order to evolve smooth functions through these frequency bins. So we have a method that is guaranteed to is proven to extract the analytic eigenvalues. Once we know what the permutations are, we can then also target the smoothest possible phase function through the eigenvectors and also get the analytic eigenvectors. So to show you some results and contrast them against what SBR2 and SMD, so the two PVD type algorithms do, I show you a rather challenging problem here. So we have 4 eigenvalues in this case. They're of a quite substantial order. So over frequency, they're quite variable. So if we run this sequential matrix diagonalization algorithm on that, then in gray, actually, you see the ground truth eigenvalues, and in color, you see what SMD has extracted. So SMD will also target a spectrally majorized solution. So the blue, the first eigenvalue is ideally always the one with the highest power. The red dashed one has the second highest power, and so forth. But as a result of that, right, so we again try to approximate piecewise analytic functions. We do the same thing for the eigenvectors as well, and underneath you see that Hermitian angle of the eigenvectors compared to a reference vector. And again, you know, where you have a piecewise analytic segment of the eigenvalues, you also have the eigenvectors roughly following the ground truth angles here. And then you have switches in between, you have discontinuities. So if you compare this now to what the analytic eigenvalue extraction algorithms do, then on top you have the eigenvalues, so they follow the ground truth, and the eigenvectors are smooth as well. So the result of this is that the approximation of these smooth functions is, of course, much easier to do. And as a result of that, for a moderately dimensional problem, you see on the horizontal axis, you see the order of the ground truth eigenvector matrix that we know, and we compare to that the decompositions that we get. So on top, we have the order of the extracted eigenvector matrix. So on top, in red and green, you have the SMD and SBR2 solutions. So they have basically this approximation of piecewise analytic functions. So they have quite a high order, and the analytic EVD is more than an order of magnitude less in cost. And these are the matrices that you need to implement as lossless filter banks in order to, for example, perform a subspace decomposition afterwards. Below you have the cost of the algorithm itself, so not the application cost, but the implementation cost of the algorithm. And you see, because it's DFT based, the extraction algorithm in the DFT domain kind of steps up with the DFT order. And again, it's actually happens to be cheaper than SBR2 and SMD. So this is kind of a little review of recent developments that we had. So with that in the bag now, let me have a look at a couple of applications. Somehow I don't actually have track of time. That's bad, right? So I think I have 5 minutes left, Marius.
Yes.
Yeah, so I got carried away there. So let me have a look at, maybe let me just pick out one application, and that's because we've already looked at beamforming, will be somewhat easy. So I've kind of introduced to you already the narrowband linearly constrained minimum variance beamformer, and its broadband equivalent underneath. If we used a standard tap delay line based implementation of this, we would do a concatenation of our beamforming filters into a vector V, and a concatenation of snapshots of our data in the tap delay line into a vector Xi here. So these vectors now would be of dimension m times l, where m is the number of sensors and l is the length of our tap delay line. So just to briefly indicate how this LCMV beamformer works, we use a generalized side loop canceller, which turns this constrained problem into an unconstrained one. From the constrained equation, we can determine what's called a quiescent beamformer, as well as a blocking matrix B. And they basically depend So with linear algebraic operations, you can derive these with matrix completion and a polynomial, a matrix inversion. And you see, if you go from the standard narrowband approach, which has WQ, B, and WA here. So WA is then an adaptive noise canceller that you apply in there. We simply go from the narrowband to the broadband simply by introducing matrices of functions. If you use the tap delay line approach, your quiescent beamformer V sub Q is an M times L vector. Your blocking matrix B is very, very large actually, and you have again following this an adaptive filter vector. So I'm sorry, I'm not going to explain this in detail how the GSC works, but just to give you an idea now of the dimensions of the matrices that emerge from this. In the tap delay line version of this beamformer, everything depends on the number of sensors and the tap delay line length L. In the polynomial version, it's really M that is the fixed factor that determines the dimensions of matrices and vectors. And the order, the polynomial order, is determined by the accuracy that we require. So as a result of this, just the way it works out is the blocking matrix, if you have not a trivial case for the constraints, works out to be the costliest component in there. And with the polynomial approach, you actually a factor of approximately L, so the length of your tap delay line, smaller in the number of multiply accumulates that you perform there. So here's an example. So we have a uniform linear array with 8 sensors. We have quite a large tap delay line length for our adaptive vector. We have a look direction of 30 degrees. So over angle of arrival, you see here now in frequency, in color, you have essentially the directivity pattern. So we preserve the look direction of 30 degrees, and we've performed nulls in directions of 3 unknown interferers here. So an interesting thing now is if you look down this look direction, the gain there, then the gain is actually pretty well preserved by the polynomial beamformer. In case of the TDL-based beamformer, we don't just have one constraint equation, we need to introduce a number of different constraint equations, each at a different frequency. And you see that at the points in frequency where we actually have defined the constraints are preserved, but they start to oscillate in between. Right, so I hope that gives you a little bit of an idea of at least one application. Let me perhaps, to stick at least roughly to time, summarize. So I've hopefully given you a bit of an idea of what matrices of functions are and how we can formulate broadband multi-channel problems with them. There's a couple of key strengths to this approach. And for me, one of the key things is really that we can take a narrowband problem and almost directly go to a broadband formulation by replacing standard matrices with polynomial matrices. What I have not shown you is in the context of coding and compaction, there's actually advantages in terms of what you can do now. So traditionally, there's been a limitation to optimum compaction filter banks to only 2 channels. So with the polynomial matrix methods, we can actually go beyond 2. And in the area of speech enhancement, where Vincent Neo and Patrick Naylor have done a lot of work, there's some really stunning results. And they simply come from the fact that with these matrix, with this function-based approach, we preserve spectral coherence, whereas DFT domain methods, which form the state of the art, create audible artifacts. So the questions that now arise might be, how can I find out more, and can I try this myself? And you'll have a couple of resources here. First of all, Vincent and a couple more of us just have an article in the IEEE Signal Processing magazine on this very topic. Vincent also has some excellent audio examples and code on his webpage, which is kind of given here. And if you want to try some of these algorithms yourself, you're most welcome to try out our MATLAB polynomial EVD toolbox. So with that, I apologize for taking a bit more time than I had intended, and thank you very much for your attendance.
Thank you very much, Stephan, for this excellent talk. So there's room for questions. Are there some from the audience? You can either write in the chat or you can also raise your hand. There's one question. Stephan, can you see it? So
I might be able to see it if I stop the presentation. Is that okay?
So this question is about, so what is the benefit of using the Z transform to solve the LCMV problem compared to an approach where you use a DFT and solve the problem by using the narrowband case for many frequency bins?
Yeah.
So that's...
Well, if you use a DFT domain approach, yeah, if you work entirely, say, in independent frequency bins, that's computationally very, very cheap. But it's not optimal in a broadband sense. And there's some nice work by Walter Kellerman, who basically explored frequency domain methods subject to time domain optimality. Also, if you look at some older work by John Schinck, I think he had some articles in the 1992 Signal Processing magazine. They're actually on frequency domain algorithms. So you have to adopt additional constraints in order to satisfy time domain optimal. It's difficult. It's difficult. With respect to your Z domain question, we use the Z domain really as a notation. Most of the algorithms like SBR2 and SMD actually work in the time domain.
Okay, thank you. So it's really, the difference is really the coherence that you lose when you do every frequency bin?
Yes. Yeah.
Okay.
Yeah, because you solve problems potentially independently in frequency bins. So these methods were great. You know, you get a very cheap solution for this, but you then have the problem that you need to stitch the solution back together again across different frequency bins. So for example, in terms of Vincent's audio applications, if you use DFT domain methods, you get artifacts. Yeah, you get some, I'm not sure how to describe this, bubbling noise or so. So it's quite audible. Yeah. So it's interesting. Yeah.
Okay. So are there further questions? Okay, there's a question by Lucas. So discretizing a matrix of function results in a three-dimensional array of tensors. And are these PEVD methods related to tensor decompositions?
There are tensor decompositions. There's, for example, a tensor SVD. They're not unique, and they're also not necessarily targeting particular structures of these matrices. So if you look back over the talk, you will notice that the particular type of structure that we targeted was of a space-time covariance matrix, but you find this property elsewhere as well. So if you, for example, multiply out two transfer function matrices, it's this para-Hermitian property. Yeah, and there's an internal symmetry that gives you or guarantees you now, thanks to understanding the uniqueness and ambiguity, a very nice structure for this. So if you use something like a tensor SVD, which is ambiguous, you don't necessarily exploit this internal structure, this para-Hermitian property. So you can do that, but you'll get a different solution. But you're quite right, and that's a question that we hear quite often. How does it relate to tensors? Yeah, and to be honest, we have not fully explored this. So that'd be a worthwhile undertaking. Good question, Lucas. Yeah.
So the slides, I think we can make them available. Yeah.
Yeah, very happy to. I think there will also be a recording. Where I understand you cut out all the unnecessary bits. You'll see what's left afterwards, but yes.
Okay, thank you very much. So there's one question I have. So when I first came across polynomial matrices or matrix polynomials, it was in a book from Thomas Skylight. So, and it was in the context of control theory. So are you aware if these methods are used in control theory, or are there some methods that you could adopt in signal processing and communications?
Well, there are a number of matrix decompositions that come out of the control domain. So for example, the analytic SVD was developed or was looked at by Bart Dumour from KU Leuven and Stephen Boyd in the context of control. And this SVD is particularly important in the area of H-infinity control. So there that matters. In the general area of polynomial matrices, there's some books by, for example, by Goberg and Peter Lancaster as well. They're often related to the control domain. So they come up with decomposition such as the Smiths and Smith-Macmillan decomposition, which, however, are different from an EVD. They target unimodular polynomials, and they have different type of properties. I think the control domain, if you think about it, they're less interested in power preservation, so less interested in para-unitarity. That's really our domain. Whereas in the control domain, often delay matters quite a lot. So you want to have a minimum phase decomposition. So the spectral factorization, for example, with minimum phase terms becomes extremely important. And I think this is where these unimodular functions tie in as well, right? So the control domain have very similar problems in some sense, but their factorizations are really targeted towards what matters in the control domain. And it's typically delay rather than energy preservation.
Okay, very interesting insight. So there's also one question I saw when scrolling down. Are there any available Python implementations for polynomial eigenvalue decomposition?
Vincent may have done some, I suspect, because Vincent's an amazing programmer, but I have not. Right? We've done everything in MATLAB.
Okay.
So have a look at Vincent's page. He might well have done.
Okay, so this is the last chance for questions. Okay, I think there are no more questions. So I thank you all for attending. And yeah, Stephan, thank you for this great talk. Yeah.
My pleasure. Thank you very much for the opportunity and for coming along. Thank you.